Let's now pick a small segment of the small segment we've already picked and go down a bit closer to the neural level. And this illustration shows conceptually the receptive field of a neuron under or immediately behind the retina. It's actually called a ganglion cell. These cells get inputs from a small area of the retina. When light falls on that retinal area, if the average illumination in the central part of the area is greater than the average illumination around the periphery, around the band surrounding the center, the neuron fires. It doesn't fire if illumination is uniform across its whole area. So these are called on-center, off-surround cells. And there are different ganglion cells which fire if the average illumination in the center is less than around the periphery, the off-center, on-surround cells. But to simplify things, we'll just think about the on-center, off-surround cell type that's illustrated. There are ganglion cells that get inputs from all the different small areas covering the whole of the surface of the retina. But let's just think about a few of these cells. And suppose the eye is looking at this scene, a rectangular image in a white field. So there's a rectangular image focused somewhere on the retina. That's a bit darker than the illumination on the retinal areas around it. Let's just look at some of the ganglion cells getting inputs from different small retinal areas in the neighborhood of that image. There's this rectangular image focused on the retina that's a bit darker than the illumination on the retinal areas around it. The cell on the left is inside a retinal area with uniform darker illumination. So the average illumination across its center is the same as its periphery, so it won't fire. The cell on the right is in a retinal area with brighter uniform illumination, but it's uniform, so again the cell won't fire. But that line of cells in the middle, part of the periphery is darker than in the center. So the average illumination of the center is greater than the average illumination of the surround. So these neurons will fire. Then there are neurons in cortical area V1 that get inputs from ganglion cells corresponding with short lines on the retina in all sorts of different orientations. So these V1 neurons will fire if there's a boundary between light and dark that's oriented on their line. In other words, V1 receptor fields correspond with what we can call boundary elements, with different positions and orientations in the retinal image. So if this were the overall visual field being observed, different shapes in different locations, V1 neurons corresponding with boundary elements around the edges of all these objects would detect their receptive fields. Let's focus on just one of the objects. V1 neurons corresponding with boundary elements all around the periphery of this object are detecting their receptive fields. So what are the recommendations associated with these receptive field detections? Well, each boundary element detection has recommendation strengths in the basal ganglia. One of the recommendation strengths is in favor of moving the eye gaze to center the fovea on that boundary element. And the boundary element also has recommendation strength in favor of placing a frequency modulation on all the V1 receptive field detections that are being made with the inputs coming from the retinal area that extends out perpendicular to the boundary on both sides. So what does this achieve? Well, go back to the oval shape. There's a boundary all around its periphery. Each boundary element recommends moving the eye gaze to center on it. So adding up all those recommendation strengths, we'll end up with a predominant recommendation to center the eye gaze on the object as a whole. Of course, there'll be recommendations in favor of other shapes in the visual field, and eye gaze will shift towards the shape with the strongest total recommendation strength, with some of the recommendations coming from other sources besides V1. Which shape is selected first will depend on other receptive field detections in other areas, like those favouring priority for certain types of shape. One boundary element detection also recommends placing a frequency modulation on the illustrated band of the retina, extending out on each side of the element. One boundary element detection has those kind of recommendations, but when you add a lot more boundary elements outside the oval, the recommended areas don't overlap. But inside the area, the recommendations reinforce each other. So if you add everything up, detection of the boundary is interpreted as a strong total recommendation that the information derived from just the area inside the boundary be modulated. And modulation of the spikes effectively means they're released for more detailed processing in area V2 and beyond. So in total, the detections of the boundary element receptor fields around a shape result in a strong recommendation in favour of centering the fovea on the shape and releasing just the visual information derived from the shape for more complex receptor field detections deeper in the cortex. So if we go back to this image for a moment and process it with an edge detection algorithm, the receptor field detections in area V1 will look a bit like this conceptually. So the eye gaze will be pulled to center on different objects because they're retinal regions surrounded by boundaries. And once centered, there may be enough recommendation strength in favor of further processing of visual information from just within the boundary, in which case the pause at that point will be a little longer.